What's up, guys? In this video we're going to be looking at magnetic effects of an electric current. This is part 2, so be sure to stay tuned for another part 3 and watch part 1 before coming here, because if you didn't, then this will look like complete Greek and Latin to you. So I'll leave the description of part 1 in the links and up here. So without any further ado, let's get started. So the first topic is force caused by a magnetic field. So we know that when a magnetic field is created due to a current passing through a conductor. But suppose if we place another magnet, suppose a horseshoe magnet nearby, will the conductor be attracted towards it? So let's look at this contraption here. We have a current passing through this entire setup. We have a conductor over here, and we have a battery, a switch, and the conductor is flowing through this conductor. And according to Oersted's experiment, we know that this conductor has its own magnetic field since the current is passing through it. So the current itself has a magnetic field, and if we place another magnet near it, this also has a magnetic field. So will the conductor be attracted towards the magnet, this other horseshoe magnet? And even if it is attracted, what is the direction and how can we find it? Well, the first thing you need to know is, yes, since the conductor has a magnetic field around it, the horseshoe magnet will be attracted to the conductor. To find the direction, we can use Fleming's left-hand rule. It helps us find direction of the motion of the conductor based on two given values: the direction of the field and the direction of the current. So these three lines are mutually perpendicular, and the thumb direction points to the direction of the motion. The index finger shows the direction of the magnetic field, and the middle finger shows the direction of the current. So by using Fleming's left-hand rule, let's come back here. So we know that the direction of the current is going this way, and the direction of the field is always from north to south. So it'd be going this way. So obviously we have the field and the current. So the motion would be this way, as this arrow over here is indicating. So we know the direction of the field is north to south. The current is going this way. So obviously the thrust of the motion would be towards this way. So in this dimension here, the conductor would be attracted to the magnet in a leftwards direction. That's all you have to understand in this concept. It's quite simple. So coming back to our diagram, we can determine that the current, as you can see here, is going this way. The field is pointing north to south. And so the thumb direction would naturally be to the left. Now, by understanding Fleming's left-hand rule, we can also talk about electric motors. A motor essentially converts electrical energy into mechanical energy, and the applications include the fans, washing machines, anything that spins around can be considered a motor. And so you may be wondering, how could an electric energy enable the motor to turn circular direction 360 degrees? That's what we're going to be looking at right now. So this diagram pretty much explains everything. We have a rectangular coil over here. Now keep in mind that the coil or the conductor could be in any direction, but for the sake of simplicity and understanding, we're using a rectangular coil. So this coil is connected to a battery. So we have a complete electric circuit, and it's placed inside the magnetic field of a north and south 2-bar magnets, suppose. So naturally the magnetic field lines would be going from north to south, and we can see the direction of the current here is moving upwards. So it'll come around here, left, straight, right, and it'd be going around here and coming back. So in this case, we know the direction of the current, we know the direction of the magnetic field, and now we just have to find out the direction of the motion. So where have we seen this before? That's right, Fleming's left-hand rule. So according to Fleming's left-hand rule, you can do this yourself by orienting your fingers according to the rule we can determine that the coil starts moving upwards. And it moves upwards until there's a half turn. And up until 180-degree turn, the current direction, suppose this is A. Let me try to make this easier for you guys. Suppose we have A, B, C, D. So in this case, we would have, as the coil slowly starts moving forward, if it makes a half turn or a 180-degree turn, then we would have A over here, B over here, C over here, and D over here. So in this case, you have to keep in mind that earlier the current was always moving from A to D. So if we use Fleming's left-hand rule again, based on the current direction, then the coil will start moving counterclockwise again, based on the rule. So essentially you have to change the direction of the current every half turn. But how is that possible? We use this device called a commutator, which reverses the current every half turn. And the brushes, they make sure that the wires aren't tangled and they ensure smooth moving of the commutator. And so every half turn the electric current changes direction. So that's pretty much all we're going to cover for this week's video. I hope you truly enjoyed and got a great learning experience. Next week we'll most likely be covering electric generator, electric induction, and if possible domestic electric circuits. So stay tuned for these upcoming videos. As always, I hope you had a great learning experience, and until the next video, this is Nishal Tube signing off. Peace.